Hi everyone, welcome back to Dave's Math channel. This is my second video on a series on probability and statistics. And today I'm going to talk about an important topic, namely Pascal's triangle and how it relates to the binomial theorem and the binomial distribution. I'll get to that later. But anyway, I think you guys are probably familiar with Pascal's triangle. It actually wasn't invented by Pascal. This is a misnomer. There's a lot of misnomers in math. A lot of mathematical results have been attributed to the wrong person. And actually, we don't know. I don't think we know who discovered Pascal's triangle, but it was discovered, I believe, in India around the 6th century AD. So it's much older than Pascal. Pascal didn't discover it until I believe, the 16th century. He was interested in probability theory, as a lot of other mathematicians were at the time. And as we'll see, it does pertain to probability theory. But here it is. So, um, like I said, I'm pretty sure you guys have seen this before. It's just a triangle. It's an infinite triangular array of numerical coefficients, numbers. And you'll notice that the numbers on the edges, the left edge and the right edge of this triangle are all 1. And then it's easy to get the other numbers. All you have to do is add the two numbers above it. So for instance, 1 plus 1 is 2. So you get the 2 in the middle of the second row. I mean, they start the rows at 0. And it's important how you number the rows and the columns. I mean, the rows are just, you start the top row is what they call the 0th row, and then you have the first row below that, second below, so on. And then the columns start the 0th column. So if you notice on the third row, they have the 0th, first, second, and third columns. And this is important because these numbers are what are called binomial coefficients. So for instance, if you want the binomial coefficient 3, choose 1. You just go to the third row and the first column, that gives you a 3. Or if you want to know a more complicated one, say the binomial coefficient 6, choose 2, then you go to the sixth row and the second column, that number is 15. So it gives you these coefficients. And you can extend this. I mean, this is a pretty big version of it. This actually has 16 rows. And so the numbers get pretty big. I mean, already the numbers are in the tens of thousands in the middle of the 16th row. And one interesting feature of the Pascal's triangle, I don't know if you guys know this, but it turns out if you add all the numbers in any row, you always get a power of 2. As a matter of fact, it's 2 to the power of the number of the row number. So, for instance, row 0, sum of the coefficients is 2 to the 0th power, which is 1. And then row 1 is 2 to the first, which is 2. Row 2 with the 2 squared, 4, 2 cubed, 8, so on. And actually, I think it's pretty easy to see why. I mean, remember how I told you you're defining the binomial coefficients. You're adding the numbers in the two in the the adjacent numbers in the row above. So you're adding two numbers in each row to the next row. So you really, if you add up all the numbers, you notice that every number on the top row contributes twice, and that's why the sum is twice of what it was for the previous row. That's kind of a nice proof by induction. But anyway, so those are some interesting properties of Pascal's triangle, and there's actually a lot more. I'm just kind of scratching the surface here, but why do we really care? And this is just an illustration of how the numbers add. I probably have to add this slide, but you just count you look at the arrows going down from the row above, and that gives you the next numbers. And so and then there's a formula. I didn't tell you this formula, but if you wanted to know, I mean, it's not practical, say, to calculate 100 rows of Pascal's triangle. That's one way you could get a binomial coefficient with, with really large numbers and a really large value n. But there's an easier way. There's actually a formula. This formula on top. N choose k. This is the symbol we use. This kind of parentheses with an n on top and a k on the bottom. That is the binomial coefficient, which we call n choose k. I didn't explain where this name comes from, by the way. The reason it's called n choose k is because imagine you have n objects, and it tells you the number of ways you can choose k out of n objects, where you don't care about their order. So, for instance, 5 choose 2. is equal to 10. 5 choose 3 is equal to 10. That means if you had, say, 5 socks in your drawer, or 5 shirts, you wouldn't want 5 socks, so that's not a number. So you have 5 t-shirts in your drawer, and you want to choose 3. How many ways can you choose 3 out of 5 t-shirts? Well, it's easy. Just the binomial coefficient 5 choose 3, and if you use this formula on top, turns out to be equal to 10. You could also get it from Pascal's triangles, they do here. But anyway, this is the formula. N choose k is n factorial. That's just the product of all the numbers up to n, the positive integers up to n, and then you divide that by k factorial times n minus k quantity factorial. Kind of a nice formula. Anyway, that's binomial coefficients, and the reason they're called binomial coefficients is because they're the coefficients that arise when you do a binomial expansion. So this slide, you probably learned this when you learned algebra at some point. You have a binomial here, x plus y. This is kind of a generic binomial. X and y are arbitrary quantities. And so x plus y to the 0th power is 1. That's pretty obvious because anything to the 0th power is 1. And x plus y to the first power is just x plus y, because anything to the first power is equal to itself. But then what if you want to do x plus y quantity squared? Well, then you'll notice that the numbers that go in front of all the products of powers of x and powers of y are nothing but binomial coefficients. They're just nothing but the numbers in Pascal's triangle. So if you look at the coefficients on x plus y quantity squared, you notice you get 1. I mean, when they say x squared, they mean 1x squared. So 1x squared plus 2xy plus 1y cubed. That's 1, 2, 1. That's the third row of Pascal's triangle. Similarly, x plus y quantity cubed gives you 1x cubed plus 3x squared y plus 3xy squared plus y cubed. Pretty nice. So that's the binomial formula. And here it is written out in general. So in general, x plus y to the nth power is just a sum. You're summing all the rows of Pascal's triangle from the 0th row to the nth. So k is just the the index for the kth row, or the kth column, I guess. It's the nth row. So you're going through the nth row of Pascal's triangle, and then you go through the columns from k equals 0 to n. And then you first thing you have is this binomial coefficient n choose k. That's just the numbers in the nth row of Pascal's triangle. And then you multiply that x by x to the n minus k times y to the k. So that's the formula. It's pretty easy to derive, actually. I'm not going to derive it here, but it's a very, very nice formula. And as a matter of fact, we can apply it. And here's where it gets nice. So I haven't really talked about probability yet. But it turns out there's a very important distribution in probability theory called the binomial distribution. And the way you get it, imagine you have a repeated set of trials where the probability of success is called P. P is just a number strictly between 0 and 1, and Q is 1 minus P. That's the probability of failure. So you're repeating this over and over. And a good example of this is tossing a fair coin. So you're tossing a fair coin where the probability of it landing on heads is P equals 0.5, and then Q is also 0.5. That's the probability of landing on tails. So in that case, you'll get P of x is equal to n choose x times 0.5 to the n, because you have 0.5 of the x times 0.5 of the n minus x. That's kind of a simple case of this. So, but there's more complicated cases. P doesn't have to be a half. I mean, you could talk about tossing a fair die. What if you're tossing a fair die 100 times? Then P is going to be 1/6, and Q is going to be 5/6. So you could calculate the probability. Say if you rolled a fair die 100 times, or if you roll 100 fair die, what's the number of ones you're going to get? If you just apply this formula, you're going to get, say the probability of getting, say, 20 ones. That's just going to be 100 choose 20 times 1/6 to the 20th power times 5/6 to the 80th power. That's the formula you use to get that. So pretty nice. And I want to point out there's actually a device. This is a nice device. It's called a Galton board. And a Galton board, all it does is just you put a bunch of little balls. You make them go through this board where it's like a triangular array of pins. And each time it hits a pin, it has two choices. It can either go to the left or to the right of each pin. So this is kind of a physical demonstration of the binomial distribution with p equals zero point 0.5. And if you have enough balls, you'll get a nice smooth distribution. Now, this red curve they drew at the bottom is a bell curve or a normal distribution. It turns out that a binomial distribution, if n goes to infinity, if n gets large, then the binomial distribution will approach a normal distribution. I'm not going to talk about normal distributions in this video. I'll talk about those later, but that's a very important type of statistical distribution. And I guess that's just a consequence of what's called the central limit theorem. If you take n large enough, the binomial coefficient will approach a normal distribution, which has a well-defined shape discovered by Gauss, Carl Friedrich Gauss, in the early 19th century. But anyway, I just want to show you some examples. So say you're doing n equals 6, and this is what the binomial distribution looks like with p equals 0.5. So this would be like if you tossed a fair coin 6 times, or say toss 6 fair coins, the number of heads you would expect, the probability of getting a given number of heads. And you can see it's already kind of close to this normal distribution, this bell curve they show. But these bars are actually, this histogram actually shows you the exact probabilities. And these probabilities are nothing but the binomial coefficients n choose k, in this case 6 choose k, divided by 2 to the 6th, which is 64. So for instance, if 6 choose 0 is 1, the probability of getting 0 heads is going to be 1 over 64. And then probability of getting 1 head is going to be 6 choose 1, that's 6 of 6 out of 64. It's quite a bit bigger. And then 15 out of 64 for 2 heads, 20 out of 64 for 3 heads. That's the most likely, and it kind of makes sense because 3 is right in the middle. But notice that even though 3 is the most likely number of heads, it's still only about a third probability of getting 20 out of 64. It's less than a half. So even though it's the most likely result, you can expect that it's probably not going to be exactly a half. And that effect increases as you increase n. What happens if you increase n? Here's n equals 10. And you can see you get a more smooth distribution. It gets closer to a bell curve the more trials you do. And notice the probability in the middle. Now the probability in the middle is only about 25%. So it's gone down considerably. It went down from about 32% to 25% when n went from 6 to 10. But it's still the most likely case that you're going to get 5. It's just that you don't expect to get exactly 5. Here's n equals 50. And now you can see it gets really close to a bell curve. And again, the most likely result here is 25, but they don't say the probability in this one, but it's probably only about 10% now. So it gets more spread out. But anyway, and you don't have to use p equals 0.5. You can use any value of p you want. And these three curves, there's one in green, one in red, one in blue. The one in blue, I think the ones in green and blue have p equals 0.5, but they have different values of n. I believe the value of n for the green curve is n equals 20. For the blue curve, it's n equals 40. And for the red curve, p is actually different from 0.5. It's 0.7, and n is still 20. So notice that from going to the green curve to the red curve, you're keeping n the same, but you're changing p. Now p is 0.7, which means that there's a 70% chance of success in each of your trials. That means the peak, if you're doing this 20 times, the peak is going to be 14 rather than 10. So it shifts the curve. And still, if you do it enough times, it's going to approach a normal distribution. It's going to be kind of a skew normal distribution. So, like I said, you can use any value of p you want with the binomial theorem. And anyway, I guess that concludes my video for tonight. So thank you for watching, and long live math, and I'll see you next time. Bye.